Okay, so the next one we're going to move on to section number 2. And the title of that is called Schur triangulation lemma. Schur is the name of mathematician, and triangulation means try to make the matrix into upper triangular. 中文通常会讲说谢尔或者薛尔的上三角化定理。Okay, so let's do some terminologies beforehand. Okay. Let's try to talk about some terms before we move on. First, although we have been using that, but upper triangular a matrix is upper triangular means that all the lower parts are equal to 0. It is a matrix such that all the non-zero parts are upper triangular and all the lower parts are 0. Okay, so 上三角矩阵, and a quick example, you can easily write down a lot of examples, and whatever the value here, as long as the bottom left is equal to 0, then this is an upper triangular matrix. And as we have been saying, the nice thing about upper triangular matrix is the eigenvalues are exactly the diagonal entries. The eigenvalues for this particular matrix, it is equal to 1, 2, and 3. And it's not hard to solve the eigenvectors as well. So upper triangular matrix, although it is not diagonal, it is good enough. Okay. Secondly, we just want to emphasize again what are the orthogonal matrices. Okay, a matrix is orthogonal means that Q is over real. Just a term means that the coefficients are real. Okay, it is a real matrix, and if you multiply Q transpose Q and QQ transpose, both of them are equal to the identity matrix. Okay, we have been seeing this several times, and it must be a square matrix, and moreover, all the columns of Q, they have the unit length, and they are mutually orthogonal. 长度是1，而且互相垂直。But now I want to emphasize another term. It's called unitary. Okay, before moving on, unitary means unit, right? The length is equal to 1. So unitary means that, means that the length is equal to 1. But it is a term specifically for mathematics. I don't even know what's the Chinese. You can search that. But it's just for mostly in linear algebra. Okay, but unitary is just to emphasize that, okay, I might consider some matrices whose entries are over C, the complex number. Now we allow some complex number. And you know, for such a matrix, then you can consider the Q star. And Q star means that it is Q transpose and then taking the conjugate on all the entries. 共二转置，你先转置完以后呢，每个元素呢都做复数的共二。Okay, so this operation we call that as Hermitian. the Hermitian of Q is Q star. Okay? And so unitary means that Q Hermitian, Q star Q and QQ star are both equal to identity. Okay, so notice that. Let me give you a sense why we do the conjugate. Okay, so let's say we have two vectors. We have 1 and I. Okay, so it's easy to see this is a vector in C2, right? When you want to calculate its length, the length of this vector, you will do the inner product of itself, of it and itself, right? So you have to do the inner product with 1, 1 and 1 I and 1 I. But notice that when you are doing the inner product for complex number C, you have to do the conjugate for the second part. So it has to be 1 times 1 plus I times I conjugate. Okay, so this part has to take the conjugate. For otherwise, it is going to be very weird. If you don't take the conjugate, it is 1 square plus I square. It is going to be 0. And the length of a vector is equal to 0. That's something bizarre. So when you take the length of this, you are basically taking the length of 1 and length of I. So it is 1 square and 1 square. So it's supposed to be equal to 2. And that's why when we are handling complex numbers, whenever it is something related to the related to the inner product, then we will take the conjugate. So if you think of this, Q star and the Q, okay, suppose Q is something like this. You have several columns. Then Q star is simply taking U as the horizontal vector, as the row vector. But you also have to take the conjugate. And from this way, you can see that this, when you multiply U1 and U1, it is actually taking the inner product of these two vectors, right? Part of the vector has to take the conjugate. So again, if you have Q star Q equal to identity, that means that U1 and U1, the inner product is equal to 1. It has length equal to 1. U1, U2, the inner product is equal to 0. They are orthogonal. And eventually you will get that, okay, U1 to UN, each of them, the length is equal to 1, and they are mutually orthogonal. Any questions or confusion about these terms? Okay, for the last part, let me use a little bit Chinese. 基本上 orthogonal 跟 unitary 是同样的事情，所以如果你今天有一个矩阵，它是实数，然后它又是 unitary 意思是说 Q 是使用复数嘛，那实数当然也是一种复数。OK， 如果你现在有一个实数矩阵，它又是 unitary， 那它就是叫做 orthogonal。OK， 只是说一般来讲，在讲 orthogonal 的时候，就是在讲 实数矩阵。一般来讲呢，讲 unitary 的时候呢，它是允许有复数的矩阵。OK， 那在下面这个状况的时候，记得你在转置的时候要再配上一个共2，才能让事情变得正确。OK， OK， so the important part is no matter you are talking about orthogonal and talking about unitary, it means that the columns are forming an orthonormal basis. Okay, the columns are orthonormal. So now, if you fall back to see the previous case, we have been mentioning that. Okay, for the basis, we can choose the basis to be orthonormal basis. So that means our Q, we can choose that as either orthogonal or unitary, depending on it is a real matrix or it could be a complex number, right? So it turns out that if you just keep doing this process, all the Q1, Q2, Q3, they could be unitary. And the product of a lot of unitary matrices, it is going to be a unitary matrix. And so eventually you have a unitary, and then this becomes a unitary. And this is unitary. So this is another unitary matrix. So that is to say, you can have A pre-multiply and then post-multiply unitary matrices such that it becomes an upper triangular matrix. And this is exactly called the Schur triangulation lemma, meaning every matrix you can use unitary matrices to make it upper triangular. Okay, so this is the Schur. Let me just say, okay, triangulation lemma. Okay, we will start with a matrix. It is a square matrix. But let's make it over C. Okay, make it a little bit general. Okay, you will see the reason later. Okay. Then this lemma tells us that there exists a unitary matrix we call that as Q, such that Q inverse AQ is equal to T. It is an upper triangular matrix. And moreover, just want to let you know, because it is unitary, Q inverse is actually equal to Q Hermitian, the conjugate transpose. And notice that the benefit of doing this is once you do this, then Q is an upper triangular matrix, and then this will tell you all the eigenvalues, right? So as long as you can make it upper triangular, then you will get all the eigenvalues at once. Okay, now let's pause for a while and think about why we need the complex number. What happens if the matrix is over real numbers? Okay, 这个定理告诉你说， 任何的 c 就可以搞出这个东西，然后那个 t 上面就会是它的 eigenvalues。OK， 那如果你现在手上就只有实数的话，会怎样？实数当然也是复数嘛，所以后面的定理全部都会对，后面的叙述全部都会是对的。但是呢，你就没办法要求说，a 是实数的时候，你其实没办法要求 t 是实数。原因是你在拿一个实数矩阵的时候呢，尽管矩阵全部都是实数，它算出来会算出一个特征多项式，这个特征多项式的系数也都全部都是实数。尽管特征多项式的系数都是实数，它的解不一定要是实数吧 ？OK， 所以呢，任何一个实系数的矩阵呢，它的 eigenvalue 不一定要是实数，所以你最后那个 t 注定就是会跑出一些负数来，所以这个定理才没有强调说前面的这个 c 一定要矩阵 A 一定要是实数。So anyway, the biggest point here is that even though your matrix A are real coefficient, the entries are real. Even if the entries are real for your matrix A, eventually your eigenvalue can possibly be complex numbers. Okay, although most of the time I give you some exam questions so that the eigenvalues are real, but it's not too hard to find one. For example, let me give you a quick one. Okay, so you can do the characteristic polynomial. It is minus x, so it is x squared minus 1 minus 1, so it is x squared plus 1, and the root of that is equal to plus and minus I. Okay, so even if your matrix is real, the characteristic polynomials has real coefficients. In the end, your root, the eigenvalues, can possibly be complex numbers. So if this one can possibly becomes A, okay, if it can possibly be Q inverse AQ equal to some upper triangular matrix, then the diagonal entries must be I and minus I and something here. Right? So even if you start with this one, eventually the t must have some complex number inside. So that's why we don't insist that at the very beginning you have to use the real. If you use the real, eventually the t is still the complex. Okay, but let me get to the conclusion that it turns out that this is actually not too bad. First of all, you can just assume that everything is complex number. It is sort of okay. At least I don't really like complex numbers, but it is still acceptable. But now, if we have a matrix A, it is over R, and we are lucky that all the roots, all the eigenvalues are real numbers. Okay, suppose we have a matrix A over R, and all the eigenvalues are real. Then in that case, we are able to say something better. T and Q can be real. Okay, so I think this could make sense. Let me write it down. Again, we still call that as a Schur triangulation lemma. And this is for real eigenvalues. Real matrix with real eigenvalues. Okay. Suppose you already know that the eigenvalues are real. So again, it says that A is a square matrix, and let's say it is over R. But for some reason, we already know that the eigenvalues are all real. Okay, then basically the same things follows, but now Q and T can be real matrices. Then there exists an orthogonal matrix Q such that, again, Q inverse AQ is equal to T matrix, and it is upper triangular. And over R. Okay? T itself is also a real matrix. And notice that because it is real, when you talk about Q inverse, it is just equal to Q transpose. You don't have to do Q transpose conjugate. You just do the transpose, then that's the inverse itself. Okay, so I hope that these two things, you are able to distinguish why we need two different theories. This happens quite several times in mathematics. Usually, you know, P implies U. Okay, P implies Q. Okay, so for example, if F is differentiable, then F is continuous at some point. Okay, you always have some statement like this. But if P becomes weaker and Q becomes weaker, then actually these two statements are not comparable. Okay， 就是你在数学上有时候你会说，那 P 弱 P 则 Q， 弱 P 则 Q， 但是当同时你把 Q， 比如说弱 P 则 Q， 那如果你现在有个 Q 条件变得比较弱一点点的时候，你当然还是可以推得到这个条件，弱 P 可以得到比较弱的 Q。OK， 但是呢，比较弱的 P 应该就推不到比较弱的 Q， 比较弱的 P 就没办法推到 Q 了吧？所以说，同时把前后的两个条件都降弱一点点的时候呢，这会变成是一个完全不相干的定理，就是没有谁会 imply 哪一个。P 则 Q 和弱比较烂的 P imply 比较烂的 Q， 这两个叙述并没有谁比较厉害。Okay, any questions before move on? Okay, let me give you an example to end today's session, and then I will give you some more time to discuss your homework. Okay, so finally we got to some matrix that is not symmetric. The eigenvalues are not real. If you have done some homework, then this matrix its eigenvalues are 1, omega, and omega squared, where omega is the root of unity, this cubic root of unity. But anyhow, one of the eigenvector is super easy. You see, always we take something like this. Try this one whenever you see a matrix, okay? Whenever you see a matrix, then you can see, okay, if you plug in 1, 1, 1, A times V is equal to 1, 1, 1, right? You should be able to do that. So lambda 1 is equal to 1. And you know AV is equal to lambda V. So now we got one eigenvector already, and I want to get a bit more. So this time, I really want to expand that into an orthonormal basis. So I want to expand V1 into an orthonormal basis. Okay, so that's the difference between previous one. Okay. I want it to be orthogonal, mutually orthogonal, and I want it to have the length equal to 1. So first thing, I have to do some sacrifice. I cannot use all the integer now because if it is orthonormal, then the length is equal to 1. So I have to divide it by square root of 3, which is the length of that. So I start with the matrix. Again, it's basically 1, 1, 1. Okay, and then I want to expand that into 3 columns, and these 3 columns are mutually orthogonal, and each column has length equal to 1. So if you have done this several times, you can imagine that this is 1, 1, 1, and then in order to make it orthogonal, you can take 1 and minus 1, right? To 1 and minus 1, then it is orthogonal. Okay, but to make it orthogonal for both of them, the third vector you have to choose properly. It is 1, 1 and minus 1, minus 2. Okay, so if you choose these vectors, then you will see that each column, they are mutually orthogonal. But beyond orthogonal, we want it to have a length equal to 1. So eventually it becomes a bit ugly. If your calculation is all correct, then your inverse, you don't need to do that because it's terrible, very hard to do that. But if your calculation is all correct, then Q inverse is equal to Q transpose. Okay, so you see that there are some trade-off, 就是交换，利益交换。Okay, if you insist that the same technique we want to use an orthonormal basis, then yeah, sure, it's much easier to calculate its inverse because it's just the Q transpose. But now, because you insist on using the orthonormal basis, so you got a lot of fractional numbers, 分数, and also, even worse, you got a lot of square root. You got root 3, root 2, and root 6. So there are some trade-off among here. Alright, but anyway, you can still do it with Q inverse AQ. And just bear with me, I did my calculation at home. So if you do a lot of calculation, then you will eventually get a matrix like this. Sorry. Okay, so you will see that the computation will be a little bit harder. And a lot of weird things coming out. But still, it follows our promise. In the end, you get a matrix of this form. And and this is lambda 1, you got an ugly A2, but still it's a 2 by 2 matrix. So you should be able to calculate the spectrum of this 2 by 2 matrix without, it's not too hard. Okay, so in the end, for A2, the characteristic polynomial is x squared minus x minus 1. So here you just do it. For example, the trace is minus 1, right? So here is minus 1. And the determinant is ugly, but eventually determinant is equal to minus 1 as well. So it's not determinant, yeah. Determinant is actually equal to 1, I guess. So whatsoever, you should be able to find the characteristic polynomial, and then the spectrum is equal to omega and omega squared. Okay, and omega is the cubic root of the unity. So anyway, in the end, the conclusion is saying the spectrum of A you can use that to make it into this form, and the spectrum is 1 and omega squared. But the point here is that you can always use the orthonormal basis to make an orthogonal matrix, and A with some orthogonal matrix in the front and in the end will give you a kind of upper triangular part. If you do the same task to the second part, you will drop it down to the upper triangular matrix. So eventually, your matrix A with some orthogonal matrix eventually will get you into an upper triangular matrix. And sorry, my mistake. You have to use the unitary matrix, and eventually you will get into upper triangular matrix with 1 omega and omega squared on the diagonal. So the matrix is not real, even though your matrix itself is a real matrix. But not too bad, we got a unitary matrix and an upper triangular matrix, although they are complex numbers.